Hi, this is Math 2510, and this video is over section 5.3, which is going to be on the fundamental theorem of calculus. And this is just the first part. There's also a part 2 of the calculus we'll cover at another time. So the fundamental theorem of calculus says roughly that the following process undoes each other. That is that finding slopes of tangent lines and finding areas of rectangular sums. These are inverse processes, basically. The first process is differentiation. And the second process is integration. To say that the two undo each other means that if you start with a function, do one, then do the other, you get the function back with what you started. And so again, like I said, they were inverse processes. The first part of this theorem uses the functions of the form g of x equals the integration from a to x of f of t dt. And so notice that g depends only on x, which appears as the upper limit in the integral. And so if x is a fixed number, then the integral will be a definite number. If x varies, then the integral also varies and defines a function denoted by g of x. So let's look at an example here. Given the function y equals f of t, and we have the graph of it on the right, we're going to look at g of x for different values of x. And the g of x is the integration of f of t. Okay, so when we look at it for g of 0, and we're looking at the integral from 0 to 0 of f of t dt. And from 0 to 0, looking at just that one point, the area there is equal to 0. And if we look at g of 1, then we're going from 0 to 1, f of t dt. So we're looking at this rectangle, or triangle, I should say, this area. And if we look at the area, your base times height, your base is 1, your height is 2, so you have an area for the rectangle there as 2, and then you divide it in half. So you have an area of, again, it's just area of triangle, 1/2 base times height. And then we look for 0 to 2, which we're going to be adding on that rectangle there. So we're looking at 0 to 2 of f of t dt. And so that's going to be equal to, let's see, 1 times 2 is 2, so it'll be 1 plus 2, which is going to be equal to 3. Then g of 3 be from 0 to 3, f of t dt. We're adding on this triangle, that area, which is just going to be 1. So we have 1 plus 2 plus 1, which would be 4. Then from 0 to 4, the integral from 0 to 4 of f of t dt. And we're now including this bottom triangle. And so that has an area of 1, but it's underneath the x-axis, so we're subtracting 1. So we're going to have the top part, which is 4 again, minus 1. So we'll be back at 3. And then from 0 to 5, we're going to be also subtracting this part, which is also 1. 3 minus 1 will be 2. So those are the areas. And then what we can do is we can actually graph g of x here. So in g is 0, it's 0. When g is 1, it's 1. G is 2, it's 3. G is 3, it's 4. G is 4, it's 3. G is 5, it's 2. And so we have this looking graph. So it starts to look like a parabola. So another one, we're going to look at g of 0. That, of course, is just going to be at 0 point. We have integral from 0 to 1, f of t dt. That's just going to be equal to 0. There's nothing underneath it. And we'll look at, 0, 0. 0 to 1, f of t dt. That's going to take in this triangle, which the height is 1. So 1 times 1, so it'd be 1/2. Then g of 2, 0 to 2. And we're taking into account this triangle, which is also going to be 1/2. Actually, hold on, that one was negative. So negative 1/2 plus 1/2, you're back at 0. Then g of 3, including these two triangles, which are opposite of each other. So, this is a half of from 2 to 3, so it's a half times 1, which is a half, divided by 2, which is 1/4. So we're going to have 1/4 minus 1/4, again will be 0. Then g of 4 is going to include these two triangles, which are also both 1/4 and negative 1/4. It's going to be 0. And then g of 5, we're including this area. This is going to include this box and then this triangle. So that box is just 1. This triangle is 1 times 2 divided by 2. That's just 1. So that whole thing is equal to 2. So we can graph this. 5, we're at 2. At 4, we're at 0. At 3, we're at 0. At 2, we're at 0. At 1, we are at negative 1/2. And at 0, we're at 0. And then we notice, with some of those, it doesn't stay 0 when we see those 0 points. So we'll have this go up some. It looks like this. It goes up to about 1/4 and down to 1/4. Right, so the fundamental theorem, part 1, says in a direct way that integration and differentiation are opposites. If f is continuous at a and b, then the function g defined by g of x is equal to the integral from a to x of f of t dt. And that will be continuous on a to b, differentiable on a to b, not including a and b. So g prime of x equals your f of x. All right, so what this is saying is that you start with a function f of t and integrate from a to x. You'll get, well, let me put it this way. If you start with the function f of t and you integrate it from a to x, then differentiate with respect to x, then you'll get what you started with, but it'll be f of x. Right? And so it'll look like this. The differentiation of your integral is equal to your f evaluated. It's basically equal to your f of t evaluated at x. Right? And so in other words, the derivative of the antiderivative evaluated at the upper limit is the integrand evaluated at the upper limit. All right, so let's kind of see how this works. Here we have the integral from 3 to x of t plus 2 dt. And we're going to show that's equal to x plus 2. And then we're going to do the same thing for 5 to x and see that it wouldn't matter what we put as the bottom limit. So I'm going to do d dx of 3 to x t plus 2 dt. And so we get d dx of t squared plus 2t evaluated from 3 to x, which is going to give us d dx of x squared plus 2x minus 3 squared minus 2 times 3. We gotta subtract the bottom, which is going to give us d dx of x squared plus 2x, and then minus 9 minus 6, so you have a minus 15. And then when you take the derivative of that, you get 2x plus 2. I'm missing something here. Put the x in. Oh, I see what I did. Okay, I see. I didn't take the antiderivative correctly. I forgot to divide that by 2. And then this is divided by 2 as well. So let's correct this. D dx of x squared over 2 plus 2x. And then that'd be 9 over 2 would be 4.5. So minus 10.5. Now when we take the derivative, we get x plus 2. which is what we wanted. All right, so now we will switch this to a 5. You know what? Let me do a different color here. So d dx, 5 to the x, d plus 2 dt, d dx, the antiderivative. Notice that it stays the same. Changing that to a 5, that won't change that. We do the limits of d dx of x squared over 2 plus 2x. That still stays the same. Minus 5 squared over 2 minus 2 times 5. Now, this is how we know that this lower limit won't matter. The only thing that 5 changes is the number here. And so this becomes d dx x squared over 2 plus 2x minus, and so we got what? 25 over 2 is 12.5, 22.5. That's the only thing that change of the limit, the lower limit changes, is that negative 22.5 from the negative 10.5. When we take the derivative of that, it's just going to be, 2x over 2 plus 2, so it'll be x plus 2. And derivative of that constant is just 0. Okay, so that's why that lower limit does not matter. All right. Now, if we look at these, g of x equals the integral from 1 to x of 2t dt. So g prime of x is going to equal just 2x. G of x equals the integral from negative 2 to x of 2t dt. G prime of x is equal to 2x. We're really just taking that small little part and putting the x in there. G of x equals integral from negative pi to x of cosine t dt. Then g prime of x equals just the cosine of x. And the last one, I think that was supposed to be a t. It won't matter. Yeah, this should be a t. G of x equals integral from 0 to x of 1 over 1 plus t squared dt. Then g prime of x equals 1 over 1 plus x squared. And again, you just substitute the x in for t. Again, all this is saying is what you're taking the integral of. When you take the integral of it and then you differentiate, you get back the same thing. And so, this is only just saying these are inverse processes. So now let's get a little bit harder with this. G of x equals 3 to x to the 5th sine of t squared dt. And we can't apply the theorem as is because we're not just taking this up 2x. This is double limits x to the 5th. So we have to apply the chain rule. So we'll have g of x equaling dx from 3, and then we'll do sine of that. So here's how we're going to do it. We're going to let u equal x to the 5th. then du equals 5x to the fourth. Okay, that's just differentiating. So we'll do 3 to u, and so here, well, we'll keep this as t squared and dt for now. All right, so we're going to take this as is, and so g prime equals sine of u squared. And then you'll have a du dx as part of the chain rule. So this becomes sine of x to the fifth squared times 5x to the fourth. We'll finalize this, sine of x to the 10th times 5x to the fourth. So we want to do d dx of x squared, an integral of 1 to x squared of cosine t dt. We'll let u equal x squared, so du equals 2x. And so this will become d dx. Oh, I don't think I changed that on the last one, but it's fine. Edu of 1 to the u cosine t dt and so this will be y prime will equal cosine of u du dx. That's what I don't need to change that. That's why I didn't know. So be dx du, and so you'll have cosine of x squared, and then du dx is your 2x. And so it'll be 2x cosine of x squared. All right. Next one, we'll let u equal 3x squared, so du equals 6x. So y prime is going to equal natural log 2 plus u squared du dx, which will give us natural log 2 plus 3x squared 6x. So we have 6x natural log 2 plus 9x to the fourth. So here we'll let u equal, well, this one's a little different, justice. So d dx is going to be negative integral from 5 to x of 3t sine of t dt. Okay, so we have to flip that integration sign, which makes it negative. Now we can go ahead and say u. We don't need to do u substitution, it's just x. So, y prime is going to be equal to negative 3x sine of x. Alright, so now we covered the fundamental theorem calculus part 1. Now let's look at part 2, and part 2 is really how we apply this theorem. And so, I did it back here when I evaluated that integral to show it. So we want to really define this out. So the integral from a to b of f of x dx is just taking the antiderivative at b and subtracting the antiderivative at a. Right, and so we want to do integral from 0 to 3 of x squared dx. We do the antiderivative, so x cubed over 3, and we evaluate from 0 to 3. And that's how we write that. We just do a line from 0 to 3. And what that means is to do 3 cubed over 3 minus 0 cubed over 3. Now sometimes, especially when your lower limit is 0, it's going to sometimes knock out what you're subtracting, which makes things a little easier. But you still want to make sure you write it out so you know everything gets knocked out and becomes 0 when that happens. So we're going to end up with 3 cubed over 3, which is going to be equal to 9. Next one, integral from 0 to pi over 2 sine of x dx. So we're going to do the antiderivative, which would be a negative cosine of x, and evaluate that from 0 to pi over 2. And so we're doing negative cosine of pi over 2 minus a negative cosine of 0. And here's one of the important reasons why you have to write this out, because cosine of 0 is not 0. As a matter of fact, cosine of pi over 2 is what's 0. This one's 0. This is equal to 1. So we get negative 0, then minus a minus, so plus 1. We get just 1. Alright. Integral from 1 to 2 of x squared plus x minus 2 over 2x squared dx. Let's adjust this some. And so there's a couple cool things here. One, we can do the integral of each part of these, but we got to divide this out into different terms. So we'll do the integral of x squared over 2x squared plus integral from 1 to 2 of x over 2x squared minus, because there was a minus sign there, minus integral from 1 to 2 of 2 over 2x squared. And each of these should have a low dx. Alright, so let's simplify this before we do it. So this is going to be 1 over 2 dx. This is going to be 1 over 2x dx. And this is going to be 1 over x squared dx. And for me, what I want to do here is adjust this so the x has negative exponents. Right, now we can do each of these. And even though I'm writing them out as 3 integrals, we can do the antiderivatives and then just evaluate them all at once. Or you can do each one, evaluate each one separately. It really wouldn't matter. So let's do the antiderivatives. 1/2 x plus, let's see, this is going to be a natural log. So 1/2 natural log x. And then this one will be, raise that to x to the negative 1. So that's going to make that a positive 1 over x. Evaluate from 1 to 2. And so we can again write this as one whole antiderivative, 1/2 x plus 1/2 natural log of x plus 1 over x, all evaluated from 1 to 2. Alright, so let me do the upper limit and then subtract the lower limit. So plug in 2, and as I'm doing this, I'm going to do any simplification. So as 2 goes in, I get 2 over 2, which is 1, plus 1/2 natural log of 2, plus 1/2. That's our upper limit. Lower limit, the 1 goes in, you get 1/2. Now, when 1 goes into natural log of x, that's 0. That's going to make that 0. And then 1 goes into 1 over x, you get 1. So this becomes, let's see, 1 plus 1/2 is 1.5, minus 1/2 is 0.5, minus 1 is 0. Oh, 1 minus 1 is 0. So you have 1.5 minus 1.5. So this just becomes natural log 1/2 natural log of 2. Basically, this and this add to equal the opposite of that. All right, next one. This is a piecewise function. So we have to break this integral up based on the domain there, where x is less than 2, where x is greater than or equal to 2. So break this into 2 integrals. First one is going to be from 0 to 2. And when we're from 0 to 2, we're looking at 3x squared dx. Second one is going to be from 2 to 5. And then we're looking at 2x minus 3 dx. So we have 2 different integrals we have to solve and then add them together. So take the antiderivative, we get 3x cubed over 3, evaluate from 0 to 2, plus x squared minus 3x, evaluate from 2 to 5. Alright, so plug in the 2, we'll get 2 squared over 3, minus 3 times 0 squared cubed, is a cubed, over 3. Again, 0 cubed. And that's that side, plus 5 squared minus 3 times 5, minus 2 squared minus 3 times 2. Okay, so 2 squared is 2 cubed is 8. The 3's cancel, so you get 8 minus 0 on this side, plus 25 minus 13 is 10, minus 4 minus 6 is negative 2. So 8, and then 10 plus 2 would be 12, which gives you 20. So a few more. We'll evaluate the integral from 2 to 3 of 2x dx. So take the antiderivative, you get x squared. You're going to evaluate that from 2 to 3. So 3 squared minus 2 squared gives us 9 minus 4, which is 5. Now, if we evaluate the integral from 3 to 2, and we're going to evaluate the negative integral from 3 to 2 of 2x dx. We're going to show that this is going to be the same as the integral from 2 to 3 of 2x dx, which is what we just found. We're going to show it by actually doing the integral with the negative sign. So we'll have negative x squared from 3 to 2. So evaluate this at 2. So you have negative 2 squared minus negative 3 squared. It's going to be minus 4 plus 9, which is equal to 5. That's why all we have to do is flip the sign to flip the limits. Alright, so integral from pi over 2 to 2 pi of secant squared x plus cosine squared x. Oh, cosine x. Cosine's continuous. Secant squared x is not continuous at places where cosine x equals 0, which is like pi over 2 or 3 pi over 2, both of which are in that integral. Okay, but because of that, we cannot apply this theorem. That is something you have to watch out for, that you're looking at things that are continuous on that limit. So if we had something like, let's say, pi over 3 or pi over 6, that wouldn't be a problem. Because secant squared is continuous between those intervals. All right, so here we have the function is negative x minus 5 when x is less than 4. 3 square root of x when x is greater than or equal to 4. Now the only issue would be if we're taking the square root of a negative number, but there x is always going to be higher than 4, which is positive, so that won't be an issue. This is another one we have to break it into 2 pieces. We'll do integral from negative 2 to 4. And that will be from negative x minus 5. I wrote that backwards. Negative 2 to 4. The x, and we'll add it to the integral from 4 to 9 of 3 square root of x dx. Alright, so we have to take the antiderivative of each. So negative x squared over 2 minus 5x integrated from negative 2 to 4. And then this integral, we're going to raise it by 1. So we'll look at x to the 3 halves. And then we divide it by that 3 halves, which is the same thing as multiplying it by 2 over 3. And we integrate this from 4 to 9. So a little simplifying here. Those 3's cancel, so we don't have to worry about that. So let's do negative 4 squared over 2 minus 5 times 4 minus negative 2 squared over 2 minus 5 times negative 2. Just doing that one, but negative 4 squared is 16 over 2 is 8, so it'll be negative 8. Remember that negative sign's not being squared. Minus 20. And then, let's see, 4 over 2, so we'll have a negative 2 plus 10. So we'll look at negative 28 minus 8 be negative 36. And that's for just this integral. Now we do the next one. Be adding it to it. So 9 to 3 halves times 2 minus 4 to 3 halves times 2. So square root of 9 is 3, so we're looking at 27, which is 54 here. Square root of 4 is 2, so 8, 16. So this would be, 48, 38. So negative 36 plus 38 gives you 2. Right. There are ways of doing these on graphing calculator. The functions here. Now we don't use the graphing calculator in our class. We use Desmos. So let me open up Desmos. And we can do a derivative directly in here. So it's just pulling up the function. Derivative integral with limits. So 0 pi divided by 2 sine of x dx. And it gives us 1, and we can name it if we wanted to. Here x. I guess it doesn't allow me to name it. I think I just let me name it g. Yeah, you can name it that way. You can't name it a function, but you can name it a letter. And create sliders for this, so we can say this a, b, and maybe call this f of x. And so we can say f of x equals sine of x from 0 to pi divided by 2. It's still going to give us 1 based on what we just put in. But it makes it easier to change then. So not so much the graph we're worrying about right now. So we get 1.57. And if we wanted to change the limit again, we can do different things. And we'll do it. So let's do the next one. Let's say b is 2, a is 1. We change what our function is. So x squared plus x minus 2 divided by 2x squared, and we get 0.347. And then if we want to do a piecewise function, this is where we would have to do it in pieces, even in this, right? So because we have to do the integral twice. May have to make this a couple ways. Let's see, g of x, yeah, g of x, and so we'll have to do a second integral. So let's call this h. And so for the first piece, we'll do 3x squared. Do that, 3x squared. For the second piece, we'll do 2x minus 3. And then we have to do more limits as well, c and d. Let me create the sliders there. This is c equals. So we have to adjust it. So our integral, we're breaking this apart. We're doing from 0 to 2, and that's going to be for 3x squared dx. And we'll have to add this to 2 to 5 for 2x minus 3 dx. So let me call this something different. L of x, there's the c and d. There are these two. And I'll call this L of x. That should work. Right. So we're doing C and D. We'll do that with the L of x being 2x minus 3. So that's going to be from 2 to 5. C will be 2. D will be 5. And so we get 12. Just that part. And then from 0 to 2, that's our A and B. 0 to 2. And that's for f of x, which is 3x squared. And we get 8. That's going to give us 20. Right. Let me do one more. Let's go back up to this one. Let's look at secant squared x plus cosine x. I'm just going to do it. So secant x, and we'll be squaring that, plus cosine x. Yes, go back and square that. Now we can see in the graph, there are absolute values, or not absolute values, I'm sorry, asymptotes in certain positions here. Again, if we are over pi divided by 3, well, there you go, pi pi by 3 to pi by 6. We get a value here. Okay. But if we do the limit we had, which was pi over 4 to 2 pi, we get it as undefined. That's because it's going over a specific piece. And so there's other methods we'll eventually get into how to do these integrals. All right, so that is it for 5.3. Check out 5.4. We'll be working more with integrals. I'll see you then.